Good morning. Good afternoon. Appreciate y'all's attention. Today we're going to talk about what happens when generative AI models begin to feed on themselves, some of the negative outcomes of that. So to start out, there's a game that we played growing up called Telephone, which I was looking online. Some people call it Chinese whispering. And this is where you are with a group of people, and one person thinks of a sentence or a phrase, and they say it whispering to one person next to them. And that person then turns to the person next to him, whispers the same thing so that no one else can hear it. And you go along the chain, and then it gets to the end, and then the last person says out loud what they heard. And usually it's quite amusing because it's pretty far off from what it started out. And just reading this paper, it reminded me a lot of these AI models playing a game of telephone with each other. And we're going to unpack what that means and how that works. So this guy here, does anyone know who this is? Yeah, me neither. So this is
I have
Ilya.
no idea. Who's that?
So this is the guy who wrote this paper. He's a guy in Cambridge, Oxford area. He seems like he's kind of junior, but he's really big on LLMs, generative AI, and getting into what happens when these models are deployed. And he published, or he was first author on this paper that came out July of this year. And what we saw was in the days afterwards, there were op-eds being published all about model collapses, don't let AI eat its own tail, is AI killing the internet, all types of things. And the cool thing about these op-eds is that they're usually written in a way that a layperson like me can understand. So anytime I get some really fancy paper like this, where I don't understand a lot of the words, I like reading the op-eds first, and they kind of give you this general sense and intuition of what the paper is trying to say. So today we're going to drive home 3 points, and those are collapsing on golden retrievers, a snake should never eat itself, and the human element is key. So those are 3 takeaways from today. That's all you got to take away. So first thing is we got to go over definitions. This might be basic for some of you all. An LLM is a large language model. You'll hear this word a lot. GPT, like Chat GPT, I didn't know this, but it means generative pre-trained transformer. Model collapse, you'll hear that a lot. And that's whenever a model forgets what the true data distribution was. They talk about this concept of perplexity a few times. And that perplexity is basically how confused a model is at predicting. So lower perplexity is good, higher perplexity is bad. There's one caveat to this, which we'll talk about whenever we get there. And then this word pronounced epic is a complete pass through the training data. So if you want to create a model, you have a data set, one epic through is the model being trained on all of the data. All right, so collapsing on golden retrievers. What does that even mean? Well, a lot of these op-eds have this example of an artificial intelligence model creating images of dogs. And on the left here, we have the original data set of all the images of dogs. So this has got all the species represented, and more common dogs are going to be more frequently represented in the data set, and less common dogs are going to be not seen as much. So we see here, we see the golden retriever twice, and we see some other unique dog species. And whenever you train a model to generate images of a dog with that data set, it, on the second batch, produces 4 golden retrievers. And some of those more unique species, like this Pembroke Welsh Corgi, is no longer seen when you ask the model to generate images of a dog. And if you do this again, it now thinks that golden retrievers are the only types of dogs that exist. And if you let the model continue on this spiral, eventually you reach this thing called model collapse, where it begins to produce these unintelligible images. They get into model collapse and what can cause this, and they introduce these 3 different types of error. There's statistical approximation error, functional expressivity error, and the functional approximation error. And these grossly oversimplified in ways that I can understand. The first one is basically sampling is finite. Just inherent to the idea of taking a sample from a population is that you're not taking the entire population. That defeats the whole purpose of sampling. And because of that, when you sample from a larger population, there's going to be information that is lost. The second one, functional expressivity error. This is that model errors are inevitable. This is a thing that happens. It's kind of how Ilya explained it. And then functional approximation error is error when we approximate a function with a function. They introduced these 3 things, but they really harped a little bit more on the first one.
Josh,
And
can you go back a little bit? I just
yeah,
want
for
to
sure.
I want to just think about this slide a little bit.
Please.
I like the wording. So functional expressivity error. And then functional approximation error. So error when we try to use a function to build a function. And that's going to be the model talking to each other. Okay. And the idea that models are always going to err. And the statistical error is that sampling is finite. Okay. All right, go ahead.
Sweet. I love it. All right, so statistical approximation error. The way they explain this is you have a distribution of your data, and then you take a sample from it. And when you take a sample from it, the information found in the margins of your data set are less likely to be taken in that sample. And they have this figure here, figure A, to drive home that point. And if we look, well, 1 second while I get my cool annotator spotlight. Okay, cool. So if we look on the right side of this figure, you start out with this data in this diamond box, and you do finite sampling, which means you can't get the entire population in your sample. So you take some of it, so it's finite. And what you have is probable events are going to be overestimated. So golden retrievers are going to be seen more often, and improbable events are going to be underestimated. So the corgis are not going to be seen as much. And then you create a model based on that data. And then if you use that model to generate data and do this again, So go through a few rounds of this. Probable events are going to poison the reality of your population, and the tails begin to shrink over time. And when they say tails, they're referring to the tails of your distribution of your data. This first part of the figure here on the left is the same thing as what's explained here on the right.
Sorry to interrupt, Cyrus. I'm really keen at following every detail. Now, how do the tails shrink? Is it towards the extremes or towards the center? Just to be sure.
Nice. So it's interesting. In this particular example here, the tails are shrinking towards the middle because you're losing that unique data. What we're going to show in a later figure is that the tails appear to be increasing, but that is due to errors. So I appreciate your question. Never apologize. And then we'll explain that some more in the coming slides. But for this sake, the main takeaway is this orange one here. Improbable events are underestimated. So improbable events, those are the ones in your tails. Those are the corgis or the random dogs that are less frequent. You're going to see those less and less. And why is it bad to lose the tail? Oh, go ahead.
And just to clarify, Obali, when we say tail shrinking, it means that what you're doing is you're reducing the area in the curve where events are more likely to happen and increasing the area where you have more rare events. And this basically means that you're going to increase the amount of unexpected answers, right? Because you're getting more answers in these areas where there's more rarity. There's unlikely results.
Okay, so kind of comparable to what we would see when we have a very small sample size.
Yes.
Okay, cool.
Yeah, nice. So they did say that. They said as your sample size approaches infinity, so as you get closer to capturing everything, this statistical approximation error gets smaller. So
which is what you would expect for any kind of modeling, right?
Totally.
Exactly. Yes.
But I'm having trouble following what Joao said because I have the opposite understanding based on this right side of the screen. Because this right side of the screen is basically showing what we talked about with the golden retriever thing, right? Where
right, exactly.
the common thing keeps happening, appears more than it should, and the less common thing.
Well, that's what I'm saying. If you think about all the possible options that the model can generate, and you have within the range of the curve, so if you have a bell-shaped curve, everything that's under the largest area of the bell-shaped curve are possibilities of answers from the model. So now, if you what the example of as you reach infinite sample, your standard error tends to reduce, and that's because you're less likely to find variations of answers. You're always going to have answers that are closest to the truth. Now, in this case, what they're saying when you end up removing this area is that the options of responses are also going to be reduced, because then you're going to start having the same kind of answer because you're coming to the point that your sample of data starts to become restricted because it's always generated by the model error. That's what I'm understanding from it. And that's what I was saying about the chances of getting a rare event are less likely. The chances of you having an appropriate response. I probably might have missaid as well, but thanks for helping me clarify.
I love the discussion. So the takeaway points from this, or why it's bad to lose that information in the tails, is that low probability events are essential for the fairness of predictions. And when we talk about models being fair or unbiased or not perpetuating different biases in our society, it's often the events in the tails is usually related to those in the marginalized groups. And then these low probability events are key to understanding the complexity of the data. So to understand the nuance of your population, you really need that information in the tails. And whenever you begin to lose that is whenever a model becomes falsely generic and not applicable to your population. All right. So
Go back. I think those 3 points are very important to understand why having this generalization of responses from AI is really bad. So the fact that you kind of shrink the tails means that you're kind of normalizing the responses. And that goes back to the point that once you start having model after model generating data for the model without adding some sort of noise to the data to allow for it to have this tails to exist, you end up normalizing the responses. And now all your responses are about the most trending data, I would say. And that's kind of a little bit of repeating the dumbness, right? So the problem here is similar to what we see in today's medicine when you have a bunch of effect estimated on samples of people that come from high-income countries, mostly white, mostly rich, or middle class to upper class, that they are not reproducible to women, to other unrepresented minorities. It's kind of the same concept here, but now you're kind of shrinking it down to a content. And then it goes back to this fairness element that you're end up going to be less and less and less fair on your description. And let's go back to images trying to recognize Black people and not being able to differentiate Black people at all, or often less relevant to marginalized groups. Again, let's try to get an LLM to reply to answers in Swahili. It's probably not going to go very well. And then low probability of events to understanding the complexity of the data. That for me is what makes me more and more concerned about this, because with this tendency to regress to the mean, to regress to the center of the distribution and less tails, you end up trying to measure everybody by the same standard, and this creates a bunch of divergence that we see everywhere. So I think that's a very important key to understand what's coming next in the paper. Cool.
Totally.
Thanks, Cyrus.
And yeah, those examples are super helpful to understand. And we talk about marginalized groups, it applies to color of your skin, at least here in the US. It applies to gender big time. And there's that case of Amazon developed their machine learning algorithm to identify who would be the best managers when they looked at all their employees within the company. And so they cut this model loose with all their employment data. And what the model found is that males are going to be the best managers. And that was because most of the managers at the time were males. So it thought that males must be really good at this thing if they're occupying these jobs. And that over time, it snowballed. So eventually Amazon killed the project and said, this is bad.
So I have a question, and maybe it's an ignorant question, but like you're describing like maybe when there is a norm or there is like a majority or a plurality, even like with the dog example, they weren't the majority in the beginning, they were just a little bit more common perhaps. So, and maybe I'm jumping to this proposed solutions too fast, but I guess that's my nature. So like if the data set is like well balanced from the start, which I guess you can argue if that's even possible. I I guess, would this happen less often, or would it just take more iterations to happen? Like, yeah, maybe you're gonna get there.
Yeah, maybe I think we might get there at the end. But the idea is, yeah, how can you maintain that original balance that was there in the start? And they've come up with different ideas and techniques to do that, to help maintain that nuance in the data. So the prevalence of those marginalized groups, how do you maintain them in the tails as you get through these iterations?
Right, like, do we need to weight them? Do we need to like oversample them?
Yeah.
Stuff like that.
Yeah, you're totally right. You're totally right.
And then the thing that these models, they did one of the bad things as well that I feel like is that they always give you an answer and they are pretty sure, they sound pretty sure on their answers for that. So think of
Mm.
it, think of you having, you're entering a bunch of data, every data has the same weight by standard, depending on the proportion of the amount of data that you have for each scenario. But they are gonna give you an answer that is pretty sure. So eventually you end up like feeding the model more and more common data, normal data, the most frequent data, and you get the most sure answer, and you wouldn't even realize that. That's another issue.
Damn, good point. Okay. Why should a snake not eat itself? In this paper, they give this example exercise where they used a model that was trained on this open source data set, and they gave it an input of text, and that's this one here. So, some started before 1360, accomplished by Master Mason, blah, 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 leading architecture design, Paris church towers, blah, blah, blah. And then they trained a model on that, and then they had a model produce data. So they wanted to produce what it was learned on, and it produced this generation 0 is the first output of the first model that was made. And it says revival architecture, a cathedral, some symbols made it in, and then some churches. And then they trained a model on that output, and they had it produce another paragraph. And it did this thing, and now we see, Brasilia makes an appearance here. Not sure where that came from. And then there's some Pope references. And this is fresh. This is generation, so this is the second time it produced something. Now we get to generation 5 and 9, and the wheels kind of come off a little bit. We see all these countries being named in generation 5, and then we see this obsession with rabbits come up in generation 9. And I thought it'd be amusing to put this text into an AI image generator and just to see what does that look like, because a picture is worth 1,000 words. So this was the original text. And if you put that in an image generator, this is probably what I had in my head whenever I read that paragraph. And then our first output is pretty similar. I'm impressed. I'm impressed. Now, when you use this as the training data, create a model and make another output, you get this. So this is the second output. And again, not too shabby. When we get to generation 5, this is where things get a little squirrely. So we have this orb floating in the sky with a bunch of flags from other countries, I think, making an appearance. I don't know who the person on the hill is. And then you
I
get to
could
generation
use this,
9.
man, in my sessions. Yes,
Generation 9.
that's lovely. Yeah.
So this was the transition here of what happens when you leave a model to its own devices.
That's awesome.
So this
There's
is
so much there's so much philosophical context that you have a bunch of rabbits around a church image. Yeah. But I'll leave it at that.
you don't have to. It'd be fun to unpack.
That's
So
fascinating.
this was the motivation for their experiment. They wanted to see what would happen with language models when they're fine-tuned with data created by other models. And in this experiment, they used this OPT 125M language model. And we talked about GPT, which was the generated pre-trained transformers. This is O is for open. So I think it means it's an open source algorithm that you can use. And then the data set is this Wikitext2 data set, which has millions of labeled lexicons and stuff for doing language type models. And they have two different methods for developing the models. They have one where they do 5 epochs, which it just goes through the data 5 times, and it uses none of the original training data. So this is kind of similar to what we talked about, Ashley, earlier. So one of them never uses the original data. It only uses the data generated from the most recent model. And then the other method goes 10 epochs, so it goes through the data 10 times. And then at each time, they re-inject 10% of the original data. All right, so now we get into the meat of the figure that they provided. And we're going to go through this kind of blow by blow. But looking at the top part, figure B, now looking at this left image here, on the x-axis, you have perplexity of generated data points. So this is the diversity or the nuance to the data points generated. And then probability is just a frequency, so it's like a histogram. And the original data is this blue one here. See this nice shape. And there is some perplexity to the data because when you look at the population, there's perplexity to people. When you looked at all the dogs, there's diversity in species. When you look at whatever data set, there's going to be nuance to it. And what they see is with each generation passing, the perplexity begins to shift towards the left. So you're losing perplexity. You're losing that nuance in your data because the most frequent data point created by your model is less perplex than the original data set. And that happened in both. So this one up here in B, this was that first one that had no data preserved 5 epochs. And then here in C, you have 10% of the data preserved and they go through 10 epochs. And you see in both cases, it moves to the left. However, that loss of data integrity or that loss of the nuance of your data is less whenever you re-injected at least 10% of the original data into your model training. Whereas the gap between the most frequent observation is bigger, or you lost more of that nuance whenever you didn't preserve the data. So that's one takeaway from this figure. The other thing the authors talk about, and this is where the conversation about tails gets a little more nuanced, is they talk about how the tails get wider as you have more generations. Now, don't confuse this with what we talked about earlier, where we said we're losing data in the tails. In the original data set, we're losing the nuance of the data, but this increase in tails is an artificial increase in errors in the data. So this is throwing in the jackrabbits. This is throwing in the @ symbols. So this is throwing in new errors into what we're discovering. So we see the tails get bigger in both cases. So the 2 points that we just talked about are summarized here. Models produce more probable sequences. That is shown by the shifting to the left, losing the nuance of your data. And then it starts introducing its own improbable sequences. That's the tails. That's the errors. So that's the left part of this figure. And I'll pause there to see what you all think.
That's great. So, one thing that I liked that you highlighted there is that they mentioned about the fine tuning. Previously, I was thinking about retraining the model from scratch. Since you said fine tuning, one thing that we might consider as well. So fine tuning for these huge deep learning models, language models, is that you take, like, let's say ChatGPT that was trained on everything. You take that final layer that gives you the output and you refine it to your task. Let's say I want to do a GPT for medical question answering. So you add a new data set that's only on medical questions, like, I don't know, from the US medical exam, for instance, and then you leverage all of the GPT knowledge for generating responses that look human. And then you add this new content for medical questions, for instance. And then this is a way for you to not spend all the money necessary, collect all the data necessary to generate a general model that is needed to answer human text, and you refine it. But doing that and redoing multiple times, as you're showing here in the figure, so generation 0 through 9, you're basically adding more and more layers to this final version of the model. So I can really see this becoming this overfitting. Like the model is just trying to memorize this data that is not representative. So maybe this speaks more also into, okay, if you want to refine something that was previously done, you can do it maybe 1 or 2 times. Otherwise, it just goes off the rail. So maybe that's one thing that we could also look at this as in, oh, let's use this model that is open source from Facebook or Meta, I don't know. But then how deep can we go into personalizing it to our intent, to our approach, before it going off the rails there?
Yeah,
I don't know.
that's a cool takeaway.
Do you guys agree? Actually, you seem confused.
I'm sorry, I'm distracted.
Okay,
wasn't-
that's fine.
That logic makes sense to me. That intuition makes sense to me. Mathematically, coding, programmatically, I'm not sure, but I like the sound of it. The other point on this figure to make is looking here on the right side. This is where my ignorance really shows. So they talk about perplexity here on the left side. And in a crude search on the internet, higher perplexity. Okay, so first, my interpretation is that it's different than this perplexity. This perplexity is the heterogeneity that you want to have in your data. This perplexity is looking at model performance, or how confused a model is at predicting the next word in a sentence. So higher perplexity is more confused or bad. So higher number is bad, lower is good. And they both start out. So the one using 10 epochs, 10% of data preserved, no data preserved, 5 epochs. They both start out here around 33, 34. And then as it trains generation after generation, you see the model that was re-injected with 10% of the original data at each generation finds this level of perplexity around 37, 38, whereas this model trained with no data preserved, 5 epochs, the perplexity hovers at a higher number, 50, 55. Getting into the math, I can explain that to you, but the authors make the point that it's nice that the perplexity was lower here when we injected original data at each round, and it's not nice that the perplexity was higher here when we didn't use original data at every round. So grossly oversimplified, but that sounded like the point made by the authors in terms of the perplexity being lower when we use some original data.
It doesn't really seem that they, like, from this viewpoint of either adding the original or not, like, are you actually benefiting for doing all of that, you know? So again, to the point of, let's reframe this model to our task. It's not even worth it to do as much. You're expending probably a lot of money to do that over and over again. And as you showed on the figures for the rabbits, you're just getting way worse responses.
You're right. You're right. You're right. And that's a good point in terms of resources being used. I talked a little bit about this is no joke running these models as many times as they are. The amount of cost needed to do this was staggering.
Jean Ricardo was talking to me about this a while when he shared the paper there that he was talking. Maybe we are reaching like the tipping point there, like the maximum output, right, Jean? That was the thing you were saying. Like maybe in 1 year or something, we're gonna run out of new data to train the models and get good results, and get to the point where you're just spending more and more money actually polluting the environment and all of that to not get anything out of it. I don't know.
Yeah,
Exactly.
I mean, for me, it makes a lot of sense, this concept of perplexity being very different when you have actual data. The way I look at this is when you're trying, again, when you're putting someone to learn a skill and you give them no additional information to learn a skill or to learn knowledge, they're just going to reiterate on the same knowledge they already have. And at some point, that same knowledge they already have is going to end up normalized, so that their ability to think outside of that small little box is so hard because they lack this variability, they lack details, the ability to get something that will inspire them to do something different. So, and if you think about that, these models have learned from all the data available on the internet, the directions for it to grow seems to me very limited, which opens an opportunity, I guess. I think we're going to see the science now go to this phase where they're going to spend some time trying to find out what is the best way that you can then get models to generate data with enough noise that they allow for improved performance. And that's going to be in a hybrid version with human data or human curation, or I don't know what's going to be, until we kind of reach a point where we now face a time where we change paradigm again, and now we're going to have a second version of AI, I think. I don't know. It pays to see, but I think this paints a very clear picture that there's something around human interaction and human production that these machines cannot yet reproduce to teach themselves. And that makes a lot of sense when you think of this from a much broader perspective. Imagine that you're doing a regression model and you now get the regression algorithm, and you use the algorithm to generate a predicted data, the predicted data is going to have much less variance and much less different values than the original data. That's how you measure the error. And so then now imagine that you get the predicted data and you use the predicted data to build a new model to predict the predicted data. And as you start doing that, you're shrinking the model performance to a point that every data you predict is going to be the same. But that's something we can play around and test out to showcase the example. Now just put that into this massive algorithms that these things are. So yeah, it's going to be interesting to see how this shapes up, and the amount of power that is needed to, get a small improvement on these technologies.
I love the comments. And to drive home, this was mind-boggling. So this is a reference they had in there when they talk about the CO2 emission needed to produce these things. So a human life in 1 year consumes 11,000 pounds of just a carbon footprint. To run one of these larger models, it's 78,000 pounds of carbon emission. And I thought the American life is 3 times, almost 4 times more than the average. But even that, it takes be 2 years of living on the earth to run these models. Anyways, ridiculous. Okay. Last thing, home stretch. And I've kind of already been alluding to this throughout, is that the human element is key throughout this process. So the authors, they introduce a few ideas in the discussion, and some of these op-eds had some fun conversations related to this. So first takeaway, access to original data is crucial. The authors found this whenever they re-injected 10% of the original data sample, and they saw the model perform better. And the literature talks about this first mover's advantage. So this is a intuitive concept, but those that created these first models using the internet, whenever the internet was comprised of only human generated content, will have better models than those generating models now, where the internet has human content and AI generated content. So those that moved first will have more accurate models. Now, this applies to ChatGPT and those models, but applies to businesses too, creating these technologies in their respective industries. So we're still at a point, we're at the inflection point where those that are embracing this technology first are going to have a competitive advantage to those that come 10 years from now, 20 years from now, and begin using the data, because it won't be all human data 20 years from now. One thing they talk about are these generative AI watermarks. So an idea to mitigate or reduce this problem of having AI generated content to train new models is attaching watermarks to any content that is AI generated, so that subsequent development of models can avoid data with that watermark and focus on human generated content only. Now, there's issues with this. This is an extra step. So companies may not want to put watermarks on their AI generated content. What's the point? Or they may say they do it and they really don't. Or their watermarks may only be visible to them and not visible to their competitors. So there's a lot of ways to twist the system, and there's not a lot of standards for this. So it's kind of the wild, wild west in terms of what practices you adopt, preventative measures you adopt. And then the last point is, again, something we've already kind of touched on, is integrating periodic resets into the training process. So rather than getting down to generation 9 with the field of rabbits, after a few generations, re-injecting human-generated content for developing your models.
Now,
All right.
this is the part where the paper really annoys me, because so yes, access to original data is crucial. And here I want to make an argument just on the way you frame this, Cyrus, that whoever gets to the market now is going to have a space. This is not us. Right? As much as we might want to put all of our attention here, this is not us. The
Right.
power needed to generate these models is something not in our reach. And us, I mean somebody who is not these ridiculous massive companies with a lot of computing power and capacity to handle this information. So
Yeah.
the market share, and I'm going to say this again, that's why people are arguing now for regulation. People are arguing for regulation because it's a market race, not because people are concerned about ethics or implications. Once this reaches the market, which is where we are now with LLMs, then now we need to recognize this, like watermarks. Yes, we need watermarks, but not because we want to improve the models, but because we want to improve how interactions and content are generated and distributed. That's the moral argument, that they're very pragmatic and technical. So yes, please, let's generate watermarks now so that we can train models and separate what's real data to what's not real data. Let's not discuss that because we're just creating bot information to reproduce biases and identity politics and all of that. That annoys me so much. But yes, that's what's going to create more structure around it. Yeah. And for me, I think that there's a direction that people are not capturing here, which is all the knowledge gained from non-English language productions. I think a big opportunity here is to try to continue improving these models by integrating technology that allows us to interpret Portuguese, Swahili, different Chinese versions and languages spoken at different parts of the world. I think that's kind of where there's a growth pathway there that could even improve more equitable access to these technologies.
Yep. And also thinking about this, maybe like 10 years in the future with all the data, what's the term? The fictional data, the synthetic data. I also feel like there is a lot of benefit to use those models that are working somewhat fine now and tailor it to our use. I mean, even at lower scales and even at like Gemini use, by connecting it to what we think are reference material that are gold standard material. So let's say we have a bunch of templates. Let's use one of these models and teach it how to write how we would like to see a template or an instruction for writing a method or something. This could be really useful, even though it's not going to be 100% accurate. And in terms for a larger use, being at the conference that I was recently, they were talking about like how these models can be tailored for enterprise use. So think of all the processes, all the information, all the metadata, the information that a company would have. Like someone is starting new at Duke and needs to do a bunch of new setup training, setup, computer resources and all of that. If you connect that database of information or do all of those instructions to one of these models, you can have a local chatbot that's going to work just nice for your company, nice enough to empower, any use that you want to do. So I do see ways of like just connecting what we have now to more resources, making more usable, more interoperable with other resources as well. And just doing that is going to be hugely impactful for other software, other types of work that we do. Not only going for the best performance possible, training it more and more and more, but just making it more connected to the things that we do on a daily work. I don't know.
Good takeaway. Good summary.
Cool. Well, thanks, Cyrus, for presenting, digesting the paper to us in a very, very